So, good morning and welcome back to NPTEL lecture series on classics in total synthesis. We have been talking about quite a few total synthesis of triquinanes, and today also we will continue and complete discussion on more total synthesis of triquinanes. Today we will start with our homegrown total synthesis, where we discuss total synthesis of 3 triquinanes, actually 2 triquinanes and one having a diquinane moiety, reported by none other than Professor Govardhan Mehta. And first let us start with a known molecule, hirsutene, and how his group has synthesized this molecule. He has used a unique reaction. Now we all know what is metathesis, ring closing metathesis, enine metathesis, ring opening, ring closing metathesis all. But in 80s, but that to early 80s, he is the one who introduced the term thermal metathesis. So, where it undergoes a retro 2+2 under very high temperature, one can even call it as flash vacuum pyrolysis to get triquinanes. So, that is a key reaction in many of his total synthesis of triquinanes and related natural products. So, let us see how he did a retrosynthesis of this hirsutene molecule. As you know, when you have a double bond, and the double bond can be obtained from alcohol via oxidation and Wittig reaction, and this can be obtained from this keto intermediate. This keto intermediate is required, which we will come to know when we talk about the synthesis. So, you can remove the carbonyl group in 2 to 3 steps, and at the same time after doing that you can remove the mom group to get the hydroxyl, and this can be obtained from the diketone. So, you can see there are 2 carbonyl groups and one is highly sterically hindered position. So, one can easily manipulate the other ketone. So, that is what you have seen in this retrosynthetic disconnection, and this can be obtained from cyclopentadiene. Okay, so, this is so well known, but I will come to that how he has done. So, it involves 5 steps to come to the triquinane moiety. First step is 4+2 cycloaddition between cyclopentadiene and 1,4-benzoquinone to get this tricyclic compound. And this tricyclic compound, if you redraw like this, now you can see this double bond and this double bond, they are close to each other, and this upon photochemical reaction can undergo an intramolecular 2+2 photocycloaddition to give this highly strained compound. Okay. Basically, if you look at this, in 2 steps one can get this highly strained compound. So, this was reported by Cookson, so it is called Cookson's dione. But what is important was Mehta's group used this Cookson dione for a very important transformation, as I already mentioned, called thermal metathesis. This upon flash vacuum pyrolysis, if you heat it at 600 degrees, this undergoes a retro 2+2. So, if you do like this, you will get this tricyclic diene dione, tricyclic diene dione. This you can also write for better understanding, better visualization, you can write like this. Clearly, from cyclopentadiene and benzoquinone, one can get this linear triquinane, okay, linear triquinane core structure basically in 3 steps. So, what are the key reactions and what are the key takeaway from this whole sequence? One, as I said, so first time the thermal metathesis was used to get this tricyclic compound. 2, people often talk about atom economy. Okay, this is a buzzword in the last 2 decades. If you look at the whole transformation, you started with 5 plus 6 carbons, and you can see in the product you have this same 5 plus 6, 11 carbon atoms, all the hydrogen atoms, all the oxygen atoms, all are retained. So, it is a 100% atom economy reaction over 3 steps. So, this is the second beauty of this whole sequence, which is group exploited in the total synthesis of many natural products. Now, let us see how this core structure was taken further for the completion of total synthesis of hirsutene. Okay. So, that was the key step. So, instead of benzoquinone, if you use 2,5, okay, 2,5-dimethyl benzoquinone, you will get this tricyclic intermediate. This upon intramolecular 2 plus 2 cycloaddition with under photochemical condition will give you this strained compound. Okay. Then you do the flash vacuum pyrolysis, you get this tricyclic compound, where compared to the triquinane which we discussed in the previous slide, we have 2 methyl groups in addition. One is angular methyl group, other one is attached to an sp2 carbon. Okay. So, how he took this intermediate to the final compound hirsutene. Okay. So, you take this diene and heat it. Okay. Basically what he wants was these 2 hydrogens should be alpha. Okay. So, he could do this using thermal condition. When you heat it, the double bond migrates. Okay. And further heating, it isomerizes to this more stable triquinane, because this is what he wants. So, by heating it for long time, you could convert this into this tricyclic compound. Okay. This tricyclic compound, he took it and then reduced both the double bonds. Okay. You have 2 double bonds and both the double bonds are reduced to get the corresponding diketone. Next, he wanted to introduce one more methyl group here. If you look at hirsutene, you have a dimethyl group at that carbon. So, he wanted to introduce one more methyl group. Obviously, if you see there is another ketone and then next to that a CH2, there also one can do the deprotonation. So, what he did, he treated with potassium tertiary butoxide, okay, and quenched with methyl iodide. So, he could introduce the one more methyl to get the gem dimethyl group, but he got only 50% yield, which is understandable because one can also methylate at this carbon. Nevertheless, you could successfully isolate 50% of the required product where you have the gem dimethyl group. After having this diketone, next, as you know, you need to remove this carbonyl group. But between these 2 carbonyl groups, this carbonyl group is more reactive, because that is less sterically hindered compared to the other ketone. So, what one can do, you can protect that. So, protection is done through reduction. So, first you reduce the carbonyl, the left hand side 5-membered ring carbonyl to alcohol, then protect that alcohol as mom ether using Unix base, you get the corresponding mom ether. Now, you have to remove the carbonyl group. How do you remove the carbonyl group? There are many methods, but he chose a 3-step protocol where you reduce the ketone with LAH to get the alcohol, then that alcohol was converted into xanthate. Okay, you treat with sodium hydride and quench with carbon disulfide and methyl iodide, you get the corresponding xanthate. That xanthate you treat with tributyl tin hydride AABN, you remove the oxygen. So, the right hand side 5-membered ring is fine, the middle 5-membered ring is fine. Now, what he has to do is to remove the protecting group, oxidize the alcohol and do the Wittig to complete the total synthesis of hirsutene. So, the mom group was removed under acidic condition to get the corresponding secondary alcohol. The secondary alcohol was oxidized with PCC to get the ketone, then simple methyl Wittig gave the final natural product, that is hirsutene. So, if you look at this synthesis, overall the key step was the photothermal metathetic sequence. So, this sequence also, as I mentioned, is one of the earliest 100% atom economy reaction. And the starting material, of course, the tricyclic compound was prepared from cyclopentadiene and 2,5-dimethyl para-benzoquinone using Diels-Alder cycloaddition reaction. Overall, this group took 12 longest linear steps to complete the total synthesis of irsutine, and the yield was about 13%. So, 13% yield for this molecule is quite competitive, and that is mainly because of the atom economy, 100% atom economy reaction. So, now we will move to another natural product which is not a triquinane, but it has a diquinane substructure plus one 6-membered ring and another 6-membered ring having a heteroatom. So, this molecule is called deoxymegalinone. Okay, you can see there are 2 5-membered rings and one 6-membered ring and another 6-membered ring, which we can call it as N-methyl piperidine. Okay. So, since we are talking about triquinanes, I just want to extend that method which Professor Mehta has used. I want to discuss the extension of Professor Mehta's methodology to synthesize such molecules. So, this was the first total synthesis reported by Professor Mehta, and in addition to the standard metathesis, thermal metathesis reaction, he has also used an intramolecular Michael addition reaction as the key reaction to construct this 6-membered ring. Okay, let us see how he has done this. First, let us look at the retrosynthetic analysis. So, this molecule, as you know, you can easily obtain from this diketone. So, if you look at the diketone between 5-membered and 6-membered, 6-membered is a little bit more reactive. So, you can do a Wittig on this ketone followed by isomerization, you will get the natural product. And this diketone, if you look at carefully, it is 1, 2, 3, 4, 5. It is a 1,5 diketone. So, whenever you see a 1,5 diketone in a natural product, immediately the Michael reaction should come to your mind. So, obviously the precursor for this could be the corresponding diketone. So, if you remove this and if you have double bond, then it can generate anion and it can undergo Michael addition. At the same time, the other side 6-membered ring, if you see, that is N-methyl piperidine, if you ozonolize this double bond, if you cleave that double bond and if you get a dialdehyde, then one can think about reductive methylation on this dialdehyde, or you can reduce that aldehyde to alcohol, convert that into leaving group, then treatment with methylamine, one can get this compound. And this compound can be obtained from here if you convert this into a methyl ketone. Okay, normally this is done using Wacker process. So, the terminal double bond can be selectively oxidized under Wacker process to get the corresponding methyl ketone, and that methyl ketone can undergo intramolecular Michael addition reaction. And this of course can be obtained from this tricyclic compound, where you have an enone and one can think about using another Michael addition to introduce this 4-carbon unit. And this of course can be obtained from cyclopentadiene and benzoquinone. So, that is why I thought I should discuss this. If you look at this whole synthesis, it also goes through the triquinane moiety. It's okay. So, this compound we already discussed, isn't it? This is obtained from cyclopentadiene, para-benzoquinone, 4+2 cycloaddition followed by 2+2 cycloaddition, you get this compound. Now, you do pyrolysis, you will get the triquinane. But if you look at the previous example, one side you do not have the ketone. So, you have to remove one of the carbonyl groups, and that is best achieved at this stage. So, this is symmetrical diketone. So, one of the carbonyl groups is protected as ketol, then the other carbonyl is reduced to get the corresponding alcohol, and basically you have to deoxygenate. Okay, the carbonyl, the keto group should be removed. So, it went through 3 steps: reduction followed by conversion of the hydroxyl group into bromide, and that bromide, during the conversion of hydroxyl group into bromide under HBr condition, not only the hydroxyl group was converted into bromide, so using a SN2 right reaction, the ketol also got clean because you are using acidic condition. Okay. So, again he has to protect the ketone as ketol, then remove the bromide under reductive condition, that is metal ammonia condition, to remove the bromide. So, now you have this. Remove the ketol to get the ketone, then flash vacuum pyrolysis at high temperature, you get this compound, and if you look at this, this is dienone. Okay. Normally you get a ketone, one more ketone here, that ketone was selectively removed using this process. So, once you have that, then the double bond should be migrated. See, basically what you need is this double bond has to come here. So, that was best achieved by reflexing or heating in benzyl benzoate at 300 degrees. The double bond could be successfully migrated to another alpha beta unsaturated ketone, but this time the double bond is tetra substituted. This double bond, if you look at this, is tetra substituted, whereas here it is di substituted. Next step is the key 1,4 addition. So, that was done using 4-butynyl magnesium bromide and cuprous bromide dimethyl sulfide complex. So, that added this 4 carbon unit, and as I said, this once you do this, next step is the conversion of the terminal olefin to methyl ketone, which is normally done using Wacker process, but before doing that you have to introduce a double bond here, is not it? Then only the Wacker process will give methyl ketone, and then that methyl ketone can undergo intramolecular Michael reaction. So, the double bond was introduced in the following standard protocol. First LDA phenyl selenyl chloride, you introduce a phenyl seleno group at this carbon, and then oxidation to phenyl seleno oxide, and elimination of phenyl seleno oxide gives that double bond. Then you carry out the Wacker process to get the corresponding methyl ketone. This on treatment with sodium hydride, it generates anion and then undergoes a Michael reaction to give this tricyclic compound. Okay. Having got that, next this 5-membered ring should be converted into the 6-membered ring with heteroatom, that is the heteroatom is nitrogen. And in order to do that, you need to ozonolysis, or you need to dihydroxylate and then cleave with sodium peroxide. Before that, one has to protect these 2 carbonyl groups. So, that was the first step, protect those 2 ketones as ketol. Then you do ozonolysis of the double bond to get aldehyde. In situ you reduce that aldehyde, you get the diol. The diol was treated with methyl chloride to get the dimesylate. So, basically what you are doing is you are converting the hydroxyl group into better leaving group. This upon treatment with methylamine, if you reflex with methylamine, it will undergo 2 SN2 displacement to get this compound. Okay. So, now what is required? You have to remove both the ketol. You have to remove both the ketol to get the diketone. Yes, that was done under acidic condition. Then selectively you have to do Wittig reaction on the 6-membered ring in the presence of 5-membered ring. Yes, you can do that, and basically the exocyclic double bond has to be isomerized, and that was done by treating with para-toluene sulfonic acid. So, though this is not a triquinane, but if you look at the total synthesis, it went through triquinane, and though that triquinane also was obtained through a thermal metathesis which was developed by Professor Mehta's group. So, the synthesis was reported in 1990, and the starting material, as you know, is a cyclopentadiene and benzoquinone, and the key step is also intramolecular Michael addition to get this deoxymagellanone. Overall, it took 11 longest linear steps, and yield was little lower, but considering the complexity of the molecule, 2% overall yield is really good, and this way he could successfully extend the methodology developed in his laboratory to extend his methodology not only to triquinane but also to other natural products having a diquinane as a substructure. Okay. The 2 natural products which we discussed reported by Mehta's group, they are racemic. The third synthesis, which is about total synthesis of another triquinane, is a chiral approach where he started with a chiral starting material called limonene, and the natural product which he synthesized is ceratopichinol. Okay, this was isolated in 1988 and it has 5 contiguous stereo centers as usual for a typical triquinane framework. So, it has cis anti cis configuration, and for him the key step is, as I said, not like the earlier 2 syntheses where he has used thermal metathesis. Here it is a chiral approach, and in the chiral approach he started with limonene as a chiral starting material, and he also used 2 key reactions. One is Johnson's orthoester Claisen rearrangement, the other one is acid mediated or catalyzed diazoketone olefin cyclization to get a cyclopropane followed by opening up the cyclopropane to get the 5-membered ring. Okay. Let us see how he did. And this natural product, first he wanted to introduce a double bond and a carbonyl group here, so that he wanted to use as a handle for further disconnection, and this molecule can be obtained from acid catalyzed intramolecular Fredolkovs-like cyclization. Okay. So, I will come to that when I talk about this, how this reaction took place, and this can be obtained from this diol. Okay. So, if you look at this diol, one can selectively oxidize the primary alcohol. Once you oxidize, this alcohol will attack and then it will form a lactol. That lactol will be oxidized to the corresponding lactone, and this can be obtained from the corresponding ketone. Okay. And this is where the first key step, that is intramolecular diazoketone addition to the double bond to get a cyclopropane, and the opening of cyclopropane gives a 5-membered ring, and this can be obtained from the second key reaction, that is Johnson's orthoester Claisen rearrangement, that can be obtained from this alcohol, which in turn can be obtained from limonene, and this process is known. Okay, this process is known. Let us see how he accomplished this. Before that, I just briefly describe the mechanism of Johnson orthoester Claisen rearrangement. So, you can take trialkyl orthoacetate. So, for example, if you take trimethyl orthoacetate, if you treat with acid, one of the methoxy group will be protonated, and the lone pair on one of the oxygen of methoxy group will push the methanol out. So, you generate an oxonium ion, and the allylic alcohol. Okay. So, allylic alcohol normally is required for the Claisen rearrangement, will intermolecularly attack this carbonyl carbon to form this intermediate. So, this again it will undergo loss of another methanol under acidic condition to give this 1,5-diene, and that can be redrawn like this, and that will undergo 3,3 sigmatropic rearrangement, which is nothing but Claisen rearrangement to give this alpha, beta, gamma, delta unsaturated ester. As you know, Claisen rearrangement will give gamma delta unsaturated ester, gamma delta unsaturated aldehyde, gamma delta unsaturated carboxylic acid. Okay. So, that is the key step, and let us see how he prepared the starting material. He started with limonene and selective dihydroxylation of this tri-substituted double bond. Okay. So, you have 2 double bonds, one tri-substituted, other one is 1,1 disubstituted. So, the tri-substituted double bond was epoxidized and then opened with sulfuric acid, dilute sulfuric acid to get the corresponding diol, and that was cleaved with sodium peroxide to get the ketoaldehyde, because if you cleave this you get the corresponding ketoaldehyde, then reduce the double bond. So, to get the isopropyl group and followed by intramolecular aldol reaction will give you the 5-membered ring with aldehyde. Then simple reduction of the aldehyde with sodium borate and cerium chloride, that is called Lucia reduction, that gives the corresponding allylic alcohol. This allylic alcohol upon Claisen rearrangement will give you the corresponding gamma delta unsaturated ester. Okay. This gamma delta antigen ester can be hydrolyzed to the corresponding carboxylic acid. Before that, as I said, you do not want the double bond here, the double bond should go inside, so that the diazoketone can be added to this double bond. So, the migration of the double bond to internal double bond was done under acidic condition, that is Lewis acidic condition. Now, hydrolyze the ester to carboxylic acid, and that carboxylic acid upon treatment with oxalyl chloride, you get the corresponding acid chloride. This upon treatment with diazomethane, you get the corresponding diazoketone. This diazoketone then on treatment with BF338 undergoes 3 steps in one part. The first step is the formation of cyclopropanation. Okay. It undergoes cyclopropanation. Okay. It undergoes cyclopropanation. Now, under this acidic condition, the cyclopropane opens, so you get this compound. Okay. So, in this particular step you can see first the diazo compound formed the cyclopropane and then it opened, and in the process a quaternary carbon is fixed. Stereochemically quaternary carbon is fixed and also formed a 5-membered ring. Then this 5 carbon unit was added, the bromine lithium exchange was done by treating with lithium, and it was added to the ketone to get the alcohol. Now, removal of the TBS will give the primary alcohol, and the primary alcohol can be oxidized and then cyclized, but you do not need this, you need a ketone, is not it. So, do a ozonolysis, you get a ketone, then remove the TBS group. When you remove the TBS group, that time one can separate these two. Okay. You can see a beta alcohol and alpha alcohol, one can separate these two. Now, if you treat with TPOP, that is tetra N propyl ammonium perruthenate, NMO is a co-oxidant, and you use catalytic amount of TPOP. So, that will oxidize the primary alcohol to aldehyde, and immediately the tertiary alcohol will cyclize to form the lactol, and further oxidation gives the corresponding lactone. Okay. So, once you have this lactone, this on treatment with methane sulfonic acid and P2O5. So, what will happen? It will hydrolyze and you will get a corresponding, you can see either this double bond or both will undergo intramolecular Pudelkopf like cyclization to give these 2 tricurettes. Okay. You can the only difference is the location of the carbonyl group. Okay. Take the required one, reduce with sodium borohydride methanol. So, this is enone, this is simple cyclopentanone, one can reduce the cyclopentanone to get the alcohol, and now you treat with lithium and liquid ammonia. So, what will happen? Lithium in liquid ammonia, the double bond will be reduced and this carbonyl group also will be reduced. So, you get a diol. This diol upon treatment with acetic anhydride you get the corresponding diacetate. Then he uses the last key reaction where in one step he removes this acetate completely, but hydrolyzes only the acetate to get alcohol. How did he do? He did with sodium in HMPA. So, this is a highly regioselective reductive deacetylation. So, the reductive deacetylation takes place here, but at the same time this hydrolyzes only the acetate to give the natural product, that is ceratopichanol. So, to summarize, if you look at this total synthesis, he started with commercially available R-limonene, a monoterpene, and then in few steps you could convert that limonene into 5-membered ring, and then he used 2 key reactions, one is orthoester Claisen rearrangement, then acid catalyzed diazoketone olefin cyclization to form a cyclopropane followed by opening of the cyclopropane to construct the second 5-membered ring, and then third 5-membered ring was constructed using acid catalyzed cyclization. Overall, he took 14 steps to complete the total synthesis, and close to 1% overall yield he could successfully complete the synthesis. So, we will have one more lecture on synthesis of triquinanes. We have already discussed many synthesis of triquinane, because if you look at the synthesis of triquinanes, there are many ways one can make a 5-member ring. So, in the next lecture we will talk about few more methods and then one more total synthesis and complete the total synthesis of triquinanes.